different screen. So you can still unmute if you have any questions, okay? All right. So these were the notes that were shared with you, and they were on the last question. And so I know yesterday I went over how you really, when you're looking at this whole list and you had to decide between being polar or non-polar, and then you had to decide between which of the three intermolecular forces was the strongest. Okay, because when we ask you, oh, which one has this one, which one has, technically they all have London dispersion, and then some of them have London dispersion and dipole, and then some of the special ones have all three, right? So when we're asking you which one it goes to, because I did get that question, I got a few emails about that, and they're great questions, by the way, if that was you. But what we're asking is what is the strongest one that is possible? All right. So so when I say that something like water exhibits hydrogen bonding in between the molecules, I'm saying that it has all of them, but it is possible to have hydrogen bonding. Whereas something like methane, which is CH4 up here, that one is not possible to have hydrogen bonding. So that's what that question was talking about, if you didn't know that, okay? All right, so when we go to look at this list, like I said, you're going to come up here. You got to decide if it's polar or non-polar, okay? So you got to relate to those notes first. So when we're looking at this first one, it says for polar molecules without F, O, or N, right? So you come up to this little part of the notes and you say, okay, a polar molecule, which is over here, that does not have F, O, or N. If it had it, then you'd be going this direction. You'd be saying hydrogen bridging, right? If it does not, then you're going dipole. So for that first one, we're going to go ahead and label it as, I just forgot what I was saying, dipole. There we go. Okay. The next one we have polar again, and now we're with F, O, or N. So polar with it is going to be hydrogen bridging. So that's how you're going to be using that little flow chart. Okay. So it was meant to help you, but I realized that later that maybe if you didn't know how to use it, then it wasn't going to help you. Okay. All right. Non-polar molecules. So a non-polar molecule automatically gets put into this category where it says it is London dispersion is the highest it'll go. Okay. That's all that's possible. So we're going to put London dispersion for that one. All right. So for the most part, those three came out fine. It was after we moved on to the word dipole, and we're like, what the heck is a dipole? All right. So dipole, di meaning two, right? So if I were to tell you dihydrogen monoxide, you guys have learned those prefixes as being two hydrogens and one oxygen, right? Same thing here, two poles. Just like we have a north pole and a south pole, a polar molecule has a positive end and a negative end, two different charged ends, right? So two different ends. And that's what it's talking about when it says dipole. So it's another way to say a polar thing, okay? So this one I said relies on dipoles and F, O, and N. So that would be hydrogen. Relies on the dipoles without that is going to be your dipole. So kind of these were the same questions that we just had, okay? And then it says relies on momentary dipoles. So you had to think about that one for a second. And momentary dipoles were listed under here for London dispersion. Now, just a reminder of what a momentary dipole is, because I explained it to you guys and I was like, oh, it's like if your parent curb checks or something and your body goes, well, like that. In that moment, you're over here and there's nothing there. Your head isn't over on this side. It's over here, right? So I was explaining that to you yesterday, but just in case it really wasn't making sense, Mr. Judd offered this little video clip that he found to some of his students. And so I wanted to show you guys right there. Did you guys see? So basically, these things are moving all over. And the minute that there was a slight chance or a slight moment where there were two positive things next to each other, they kind of went in, right? They're like, ooh, repel. So these things are not these big solid atoms do not have a solid cloud. They are a fluffy cloud. They are movable, all right? Just like you see the clouds in the sky, right? And so just like that, we saw that this thing moved when it needed to move, okay? It was random and it was a brief disruption of charge distribution, meaning now there's a positive end and a negative end and things kind of move, okay? And as this one got closer with that positive and negative end, that made these two things switch. It made all the positive end stuff start pushing, and this stuff is going to start turning, all right? So these things are very movable. And so if you keep watching it, what we end up seeing is that in that moment where there was a positive and a negative end for different atoms or different molecules, nonpolar molecules, now there's a reason that they're attracting to each other. And when we get a bunch of these attracting to each other, they stick together, and now we have a cup of water, all right? Oh, I shouldn't say that. Oh, sorry, not a cup of water, but you have a state of matter, whether it is a solid or a liquid. Water has hydrogen bonding. All right, so that's what London dispersion is. It's the fact that these things are just constantly moving and redistributing themselves and kind of deforming each other in order to give each other these different poles, okay? And once you have poles, once you have a dipole, then you have attraction. That's an intermolecular force. All right, so back to this. We have momentary dipoles, so that was London dispersion. This next picture, you had to think a little bit. Is this a polar molecule? It's definitely not one of our basic shapes, so we're not even going to worry about the shape. We're just going to look this and look at it very generally. So take a step back from this picture. So let me show you the image. Sorry. Just so you know, that little video that I was talking about, it was playing and I didn't realize that I didn't have the screen shared at that moment. Sorry. So all that I was showing you was that these things are moving around, and so now they have a positive and a negative end, and now they're going to be attracted. Okay? All right. So back to this question. We have to take a step back from this picture. We have to look at it, and it's showing something that doesn't look very balanced, right? It looks kind of lopsided. It's not evenly spread and all that stuff, all right? You also know that yesterday I kind of drew it out for you that all your electrons can be on one side. It's kind of what we just saw again here, right? When we have electrons all on one side, we have that negative and positive side. All right. So here, all of your electrons are not going to be evenly distributed. They are going to be kind of lopsided. So that tells us that this is a polar molecule. So once we establish that we have a polar molecule, then we have to ask ourselves, is there fluorine, oxygen, or nitrogen somewhere in there? In this molecule, we do have an oxygen present right here, and there is a hydrogen. That tells us hydrogen bridging. Okay? All right. Then for this one right here, we have CH4. So we have the hydrogen there, but looking at this, what CH4 looks like, this is a tetrahedral, and these are all the same on the outside, meaning they're all pulling in opposite directions, right? So this is a non-polar molecule, therefore London dispersion. Okay, so again, keep using your little flow chart here to help you answer those. And then for these last three, because you might see those again, I think everyone got the intra and inter, so I'm just going to put those in there. So intra is inside, inter was in between, just like the internet takes you across the district, so you can have school to school to school to across the country to across the world, right? And intra is just within your little school. Okay. All right. PF3. All right. So what I would have done with this one, unless you wanted to draw it, which if you did, I'm really proud of you and I love you for that. Okay. But PF3, when you look it up, you get this image that pops up. So you have 1, 2, 3. It is a trigonal pyramidal because of that lone pair up there. That is always polar. That was something Miss Lever went over with all of you guys. So always polar. So we have to ask ourselves, is it dipole, dipole, or hydrogen? F, O, or N? Well, hopefully you're like, yeah, there's an F, of course. But I'm going to stop you there because there is no H. There is no hydrogen. And the whole thing is called a hydrogen bridge, which means you probably need to have a hydrogen there. So it is not going to be hydrogen bridging. This one is actually dipole, dipole. So when you see that one later today, make sure you don't forget that one. All right. H2O, okay? H2O is bent. You've seen that one a couple times with 2 lone pairs, right? So that's automatically polar. And we have that oxygen with the hydrogen. So hydrogen bridging, okay? And then finally, the last one was N2, which I have kind of talked to you guys about a couple times because we keep getting asked, how many are they sharing, right? That was been our discussion for the last couple days. So remember, they're sharing 2, 4, 6 electrons in the center. But if you look at the whole image itself, it is a nonpolar molecule. They are balanced on the outside. So nonpolar should tell you London dispersion. And that was that last answer.